Welcome for the part 2 discussion on galvanic corrosion. The part 1 discussion on galvanic corrosion, we raised certain issues of like, can we predict galvanic corrosion or not if you have two metals? If we can predict, can we determine the galvanic corrosion rates? And if these two questions are answered, then we said that you need to know what are the factors that control the galvanic corrosion. And if you know what are the factors or parameters that control corrosion, that affect corrosion, then it is easy for us to propose methods to avoid or to prevent the galvanic corrosion of the metals. We also need to look at the evaluation of the material for the application against the galvanic corrosion. We have seen the first aspect clearly in the earlier class. Can we predict if two metals will undergo galvanic corrosion or not? What is the criteria for that? What is the criteria to show that, okay, I have given you, let's say, stainless steel and maybe a steel, between these two, one will be galvanically corroded. What is the criteria for that? It is a potential. What is the potential called? It is the galvanic potentials or the corrosion potentials. So we seen in the last class that the galvanic potential is the primary reason for making one metal as an anode, the other one as a cathode. We also just started discussing on how do you really predict the rate of corrosion. We look at the events diagram, all right. We look at the events diagram, taking an example of clearly a noble metal and an active metal. We took, for example, I think the platinum, right? We took platinum and then used the events diagram to find out what happens if you can couple them galvanically with the other active metal. You know, we gave only schematic thing there. We didn't give really actual values. I think we used for steel, I suppose, steel or iron is talked about. Now, we also said that in the case of platinum, the equilibrium that we deal with there is the I would say maybe H plus H equilibria, or maybe oxygen and hydroxide or water equilibria, for example. We are not really concerned about the platinum ion and platinum equilibria because it's too far from that. And then we also look at the equilibria of what? The equilibria of the active metal, in this case maybe iron and iron ions, and the corresponding Tafel lines, and see how the mixed potential theory will ultimately lead to the ECAR value of the platinum and the steel when they are coupled. What is the corresponding ECAR value? How does you get it? The same, the mixed potential theory is valid here. The total amount of cathodic reaction on the system is equal to the total amount of what is that other reaction? Anode reaction. So that is the criteria. If that is the criteria, then you know what is the corresponding ECAR and ICAR values. We also said that if you are going to shorten platinum versus steel, the ECAR value of the couple I mean the ECOR value of the iron goes up, and so the anodic dissolution increases. We also say that the hydrogen evolution on steel or iron decreases, whereas the hydrogen evolution on platinum significantly increases. So these are observations that we made. In practice, we don't normally see a noble metal being shorted with active metals. We normally see metals which are generally active in nature. We are not talking about it. Okay. Say some examples. Practically, you will see. You may have, let's say, steel. You may have stainless steels. Or you may have copper-nickel alloy. You can have steel. We were talking about one of the prevalent place of galvanic corrosion is what? Is the heat exchangers. In the heat exchangers, you can have a steel shell, the stainless steel tube. You may have copper-nickel tube and steel as a shell. You can have. You can also have titanium, and you can have steel, titanium, stainless steel. These kind of combinations are quite common. Okay, and so you are going to talk about really two active metals when they are involved. How does the corrosion take place? Now I am going to now talk about here between two metals, which is, let's say, I will call iron here, which is somewhat like steel. I talk about a steel combined with the zinc. In practice, it is not the situation here. You have a galvanized coating, but I don't think zinc is used as a structural material. There may be some zinc die castings, but otherwise structurally zinc is not used as a good material of construction. I taken zinc for one important reason, to show that ICOR is not important in the galvanic corrosion. You have two metals like a steel and zinc. If I have assumed that the steel has got high corrosion rate and zinc has got low corrosion rate, that is not going to decide the galvanic interaction. What is going to decide is the galvanic potential. That decides which is going to be made anode, which is going to make it as cathode. So that is the reason why I chosen to illustrate how the galvanic interaction occurs between, say, iron, or you can call it steel, and the zinc. Now, how do you proceed with? You proceed in a very simple, similar manner, like you draw two Evans diagrams, right? The Evans diagram for what? Evans diagram for the steel, the Evans diagram for zinc. You just first you need to make them, right? But when you're making this, be clear about what in Evans diagram, what are the things required? You need, what are, like exchange condensity you required, Tafel lines are required, Tafels are required, the equilibrium potentials are required. Okay, these are the things that are required actually. So what you can do is you can construct an Evans diagram for zinc and iron separately or independently, and find out between these two which will undergo more severe corrosion, and when you short them, when the galvanic interaction occurs, right, what happens to these two metals. Okay, and so I think you can work independently now. Isn't it? You can start drawing the diagrams, but keep in mind the one important factor. What is the difference between zinc and iron? We discussed, I think, which will undergo more corrosion. Zinc will undergo more corrosion, or iron will undergo more corrosion, let's say in an acid solution. Yeah, which of the two? Or maybe in a, let's say in a sodium chloride solution, where the hydrogen reduction reaction is the cathodic reaction, okay, other is the metal oxidation. You tell me which of the two metals you expect to corrode more? Iron. Why? Yeah, so the exchange condensity for hydrogen equilibrium with H plus on zinc is much lower as compared to the exchange condensity for H plus H on iron. It's about 10 power 3 times difference. Okay, so then you can, now we can draw, okay, a typical, or I would say a schematic device diagrams representing iron and steel and show how the corrosion taking place. So I think you should draw parallelly and see how you are getting these things now. So I am just going in a very simple manner, and there is nothing very complicated here, right? So I represent now the tafel lines for hydrogen reduction reactions. Okay, I will do that. So which is what? Which one corresponds to iron and which one corresponds to zinc? The right one corresponds to? The exchange condensity for Fe2 plus Fe and zinc 2 plus are almost the same, 10 power minus 6 or so. So it's not going to change much actually. So I've just drawn a kind of representative diagrams. Okay, which one will corresponds to zinc? Which is the one correspond to iron? The low one. So this corresponds to zinc, right? I naught zinc 2 plus and zinc. And what is this? This is corresponds to A naught, right? Now you can find out what is the corresponding corrosion rates, right? And this is the I got zinc, all right? What corresponds to iron? The iron comes somewhere here. See, please again label that, because you have to label these things, otherwise it will confusing. This corresponds to and this corresponds to electrons, right? And these two are corresponding to what? This is corresponding to and I just put an arrow here. This corresponds to right. How do I proceed further? How do I know when you do a galvanically shorting them, what will be the resultant corrosion rate of iron and zinc? How do you proceed? I have to add the oxidation of both the oxidation curves, and I have to add the reduction curves corresponding to both the metal surfaces, right? So I do that, okay. So what you can do is you can just add these two, right. And this corresponds to what? This corresponds to hydrogen evolution on both zinc and iron, correct? And similarly I can do this corresponds to total anodic. So what is happening? Now it is this intersection point of this, the mixed potential theory is now valid, right? So I draw a line connecting all of them. Then I draw this line. What is this potential called? This is of E car of iron and zinc couple, right? This is the I car of iron zinc couple. Total corrosion rate is increasing actually, right? I hope these lines are clear to you now. So can you tell me, that means what happens? I take a zinc, I take zinc and I take iron here, I determine this corrosion potential of that, corrosion current of this. Now I put them together, I just short them like this. When I short it, will the potential of iron and zinc will be similar or different? The similar because it's conducting, highly conducting. So the potential of these two are going to be similar, right? That potential of this corresponds to what is given in the Evans diagram as E car, iron and zinc. This is what you are seeing this here. At that particular potential, what is the current that is flowing on steel and zinc is given by this diagram. Now can you get from the diagram, what is the one that corresponds to the dissolution of iron? What is the one that corresponds to dissolution of iron? And what is the one that corresponds to the dissolution of zinc? Can you people tell me in this, what is happening there? Yeah, So the line, the potential line intersects now, where does it intersect? It intersects all the lines. It intersects the cathodic reduction curve of iron, zinc, anodic current of iron and as well as zinc, right. So that particular intersection point gives you what is the corresponding reduction reaction, oxidation reaction in both cases, okay. So what is happening now? Now what is happening now, you see what is happening to the hydrogen evolution on zinc, The hydrogen evolution on zinc is getting reduced to this value, am I right? It is reduced from here to this value is getting reduced, right. The hydrogen evolution is decreasing from here to here, but what is happening to corrosion? The corrosion of zinc is moving from here to this value, am I right? So zinc is now getting oxidized more. So this is the ichor of zinc when coupled with iron, right? No, I'm sorry, nothing wrong actually. Yes, it's wrong actually, right? Okay. No. Yes, correct only. Yeah, I'm sorry. Yes, correct. Yes, correct. So it is that of the zinc here is correct, right? So this is the zinc dissolution rate given here, and this is the dissolution rate of the dissolution rate or ichor of iron, zinc actually, right? So the iron corrosion rate is decreasing from this point to this point, am I right? And the zinc corrosion rate is increasing from here to this, okay. So what do you call this process? You discussed about one protection before, the electrochemical protection of a metal, right? What do you call this? The sacrificial protection. It's a cathodic protection of the metal by sacrificial action. Zinc is getting dissolved at the expense of iron, right? The iron is getting protected here, okay. So look at these diagrams. It's a very busy slide, I would say, busy diagram actually. You have several information that you can draw from here. If in fact you understand this, you have understood the mixed potential theory in completion. I don't think you will have a problem because it's the most complex image diagram that you can think of actually, okay. Now you know that the dissolution of iron is getting reduced from here to this. Zinc is increased from here to this, okay, is increasing here, okay. No, sorry, zinc is moving from here to this actually, okay. So this is what happens. Now you look at the kinetic factors that influence the corrosion of zinc. What influences the corrosion of zinc in this? Can you just tell me more? Each of them influence other one, right? Iron influences zinc, zinc influences iron, right? You have iron has got two table kinetics. One is the anodic kinetics corresponding to iron dissolution, please understand. You have a cathodic kinetics corresponding to H plus giving rise to hydrogen. Iron has got two kinetics. For the zinc to dissolve, which of the two kinetics influence very severely? Yeah? Hydrogen evolution iron is severely affecting. That means the beta C of hydrogen evolution on iron is severely affecting this. Agreed? Then look at from the zinc point of view. which kinetics of zinc is affecting the galvanic corrosion of zinc. Zinc has two kinetics, couple kinetics. One is hydrogen evolution on zinc, right? Other is the zinc dissolution, zinc to zinc 2 plus, right? Two tablet slopes, beta C for zinc dissolution and beta A for the, beta C for the hydrogen evolution on zinc and beta A, which is the oxidation of zinc taking place. Beta is okay. So the beta A of zinc is getting influenced more. So please notice the beta C of the noble metal, I can generalize it. When I say noble, I mean relatively noble. So the beta C of the relatively noble metal, beta C of the relatively noble metal and beta A of the relatively active metal decide the galvanic corrosion rate. Can you say that actually? The beta C of the relatively noble metal, beta A of the relatively active metal decides the galvanic corrosion rate, right? Similarly, the I naught for the cathodic reaction of the noble metal is more important than the I naught of the cathodic reaction of the relatively active metals. Similarly, you talk about I naught of the metal oxidation to metal reduction, you talk about it is more for the active metal than for the relatively noble metals. So this diagram that you see here, it talks about what are the governing factors for controlling the galvanic corrosion. Can we predict the corrosion rate? Can you do it? If I give you these all the table parameters, exchange current density, is it possible for you to calculate by solving the equation what will be the corrosion rate of iron before coupling with zinc and after coupling with zinc? Is it possible to do that by solving the equations, or not possible to do that? I want an answer from you. Possible? So it's possible. So it is possible to calculate the corrosion rates based on the mixed potential theory, based on the Evans diagram. Okay, what will be the corrosion rate of the galvanic couple? Okay, in two different metals are existing at all. All we need are the independent governing equations. Yeah.
The metals are coupled.
Yeah.
Or in this case, we have considered hydrogen evolution.
Yeah.
So hydrogen is getting involved irrespective of oxidation of iron or zinc.
That's right. You can add one more complication. What happens suppose I have oxygen in the system? It's a unique question. Eh? When metal is corroding in water, you still have. So you need to add one more complexity to that, right? Add one more to this. You can solve the equation, right? You can write an algorithm and solve it. It's not that difficult for you to do this. In fact, people do it. It's not that in academic exercise people do in the field. How the corrosion are taking place in the galvanic conditions, right? So it is possible people do it because there are practical problems existing in the field. Okay, so they use these governing equations to solve the galvanic interaction between the two different metals are done actually. Okay, to say then what kind of a life is possible, all this you can do this with this equation. I hope you are able to get this clarity in this Evans diagram. If not, you please have a look at this, go through more closely. If you have any problem, you please do let me know. Okay, if you understood this Evans diagram, I think you have understood almost all the complex Evans diagrams that are possible in the corrosion processes of metals, whether galvanically taking place by Corrosion process, pitting process, or all are following the Evans diagram, the kinetics of that actually. Okay, if you are clear, and if you have any questions, we can move forward. Okay, anybody has any questions, you please let me know. Yeah.
How do we get the line corresponding to the total anodic reaction in the given graph?
Huh? The total, what do you do? See, the current varies with respect to the potential, right? So what I do? Let us take the case here, let us take this one. This corresponds to what? This corresponds to ion dissolution. This is the equilibrium potential. When I move the potential to higher value, suppose I move the potential, I move it to here, for example, I move to this place, okay. This corresponds to this. How do I get this? The Tafel line, right? Eta is equal to plus beta log I by I naught, right? I can calculate. I know the equilibrium potential, I know applied potentials, I can calculate, right? So I get this line. I get this line. Now at this given potentials, suppose let us take this particular potentials, I know this is the amount of current for ion dissolution, this is the current for zinc dissolution, that is the total current I am going to get. Suppose I take iron and take zinc together and pass current, I apply same potential, if I use an ammeter, that is the total current, I will get it. So I simply added these two, okay, and in a graphical way, but you can also do it by solving the equations by applying various potentials, right? You know the equilibrium potentials, you can keep on at different potentials, you can able to do that, okay. So graphically you can do this, you can also do by writing a proper algorithm and getting these values without any problems, okay. So that's what I have done it, okay. See, I have not added here, please see here, below this is only one current and above this only the current goes up, right. So I have just done a simple common, I would say, sort of understanding that how this will work at all actually, yeah. See, please here, this is a log scale, huh? The log scale is, marginal means it is a log value, right? Assume that it is 10 power minus 4 and it is 10 power minus 3, you add it, what happens? So it will be, 10 power minus 4, 10 power minus 3 is going to be 1001 for example, okay. So in graphically speaking, this is a log scale. If it was a linear scale, it would have just pushed equally, right? So this is a log scale here. That is why you are getting this small variation. Otherwise, it is a significant variation that you are seeing that, okay. Of course, compared to this is a small variation, no doubt, because it is a log scale at all, okay. So please notice that this is a log scale. That is why we added here, okay, only small. In fact, if you look at more closely, you may not even go to this value. It must be just touching the line only, because it's 10 power 3 times higher. So it is going to go into the third decimal point. So it's going to be less only actually, okay. So basically, it's a log scale. That's what it is. Yeah. Shall we move? Okay. So this is how you understand and you can predict the calculate the corrosion rate of the metals. Let us make it a little bit more complex. Assume that the system is passivating. The passive systems are, can you give an example of a passive system? Stainless steels maybe in sulfuric acid, okay, titanium cannot be this, okay. Let's take the case of a stainless steel in acid solution. It is deaerated, it is not aerated. So what happens in that case? It undergoes what? It undergoes active passive transitions. We have seen somewhere before, but it's a different way of interpreting today, okay. So stainless steel in deaerated acids. I am not talking about pitching at all, just I will talk of passivation, okay. Let's take this what I am going to do, okay. So this is corroding here, the metal is undergoing this is, let us say, I naught H plus H on stainless steel. Okay, this is an active passive dissolution, and you guys know that it is an icar. This is your car. To make it pictorially, I say taken a material, an acid, let's say sulfuric acid, dilute sulfuric acid, with stainless steel, so this is the E-car. If I measure with a reference electrode and I get this E-car, and if you carry out polarization diagram all, you get something like this actually. What I will do, I am going to now insert a platinum and I am going to short this. Okay. So what do you think will happen now? In order to know what to happen, what you should do now? I should draw platinum. So I should do one for platinum. What I have done for this, I do one for platinum. Okay, I do something. I naught, okay, on platinum. So what do? You just sum up these two. So what do you think happens now? Corrosion decreases, right? The corrosion rate significantly decreases because of the galvanic action, right? So you can see that the corrosion rate moves from there to this. It is due to what? It is due to icar of stainless steel platinum. Understood? For some reason, assume that the line is going to lie somewhere here. Assume that line is going to somewhere here. What happens? What will happen? Increases. So it depends upon what extent the exchange current density is increasing. If the exchange current density is not increasing adequately, you could have a situation where the corrosion rate would increase, right? Let's go to the situation here. Now is moved from here to this. Does it reflect something we discussed earlier? Is it cathodic protection? Is the potential is moving cathodic? Huh? It's moving anodic, right? The potential is moving anodic, so it is similar to an anodic protection. In anodic protection, you are applying an external current by a potentiostat. Here, you just use a platinum. The platinum can enable, okay, the passivation of the metals. Possible. I am not saying doing, but it's possible that you can do. If this current is adequate enough to cross the nose of the diagram, nose of this particular polarization curve. That's of course is critical, right? So it's possible to do this, okay, and this is happening not here. This happens in the case of titanium and platinum. It happens in the case of titanium and platinum. We can take a titanium. The reason is that the EP is quite low for that. It's very low. The critical current density for titanium to passivation becomes very small. So you don't need so much of current required. Okay. So the platinum, it does help. So titanium platinum is a well-known example of industrial use. Industrially it is used. How is it used industrially? I'll just give slightly different. Okay, the people do this is called as titanium platinum alloys. Okay, here small quantities of small quantities platinum is alloyed. You make an alloy, the metallurgists know, right? You take titanium, put platinum to that, you melt it, and this undergoes passivation. How does it go? I have, let us say, okay, and I this is your titanium alloy, and I have very small amount of platinum that I have. How does it work? Initially, in this case, okay, as I told you before, I have this. Initially, what happens? You get something like that. Now, as the titanium dissolves, what happens? Platinum gets enriched, right? Okay. Now, what happens as the titanium getting enriched? What will happen to this line? This line will start. Am I right? So this will move as titanium gets corroded and platinum gets enriched. So what will happen in this case? Beyond certain point, the platinum will beyond certain point, the titanium will spontaneously passivate. I don't need to pass any external current, okay, because of this. So you don't put too much of platinum in the beginning. You put small platinum, okay. As the titanium dissolves, enrichment of platinum occurs, and so the cathodic curve starts shifting towards the right side and ultimately leading to passivation. Corrosion, right, isn't it? With mechanical action, the titanium and platinum will go together, right? It won't remain. Platinum also will just get knocked off. Because platinum is noble, it doesn't dissolve, it remains on the surface, and so it gets enriched. Okay? So, and this term for this is called as noble metal alloying. Mostly sulfuric acid, huh? Yeah, reduction reaction is hydrogen only. In sulfuric acid, right? What is the reduction reaction? Is a hydrogen reduction reaction actually, right?
Reduction reactions that you are drawing, these are the combined.
Yeah, of course you can put a platinum and draw it. I've just simplified all this actually, okay? Put that. So this you can say, if you want, is called as a noble metal alloying, and so the principle is like this only. So what you need to look at here is analyze the situation. Okay, how does the galvanic interaction works? Okay, it could work if it is going to be purely noble metal and active metal, two different active metals, or you can have a noble metal and a passive metal and an active metal. You can have all kind of combination. You don't have to worry. You just have to draw the Evans diagram and then find out what is the resultant galvanic corrosion can happen in the metal actually. Okay, so that's the way you should proceed in computing the corrosion rate of the galvanic couples. Okay, is it clear to you? Okay, so far we have seen the influence of the electrochemical factors on the galvanic corrosion of two dissimilar metals. If I can summarize, what are the factors that one should look into when you are computing the galvanic corrosion, I think that will be very useful. The following factors, electrochemical factors. We have seen 3 different cases: active metal and a noble metal, 2 active metals. In another case, a passive system and a noble metal combinations. If I summarize, okay, what are the governing kinetics in each case? We can say that the cathodic kinetics of what metal you think, which of the two, the noble or active metal, will influence the galvanic corrosion. The cathodic kinetics of which one? The noble metal, okay, of noble metal. Two, the anodic kinetics of which of the two. Okay, I would put it as active, or I call as relatively active. That way, you can even call this is noble, or what do you call it, or relatively noble, right? Noble, or it could be relatively noble. When you say this kinetics, what do you mean by that? What are the parameters you think? The broad, right? Kinetics means what are the parameters you think? What are the things that will take into account? The kinetic parameters are what? One, the exchange current density, right? 2, what is that? It is the equilibrium potentials, or you may even call it as a corrosion potentials. What else? Third, Tafel slopes, right? So if you can look for these informations with respect to the relatively active metal and relatively noble metal, and you get these parameters, you can calculate what can be the galvanic corrosion rate of the relatively active metal, right? So that can be done without much of a difficulty. Any questions here? Okay.